All right, so we are finally down to the last lecture in this course, and it's not going to be on any quiz or anything like that. So this is just for fun. You learn some facts about the history, early days of computing, and some very exciting stuff that happened at that time, which actually has made your life much simpler, because you'll get a feel for what it might have been like programming in those days. So this word is used a lot, stored program, computer, because the program itself is stored in the machine, and that was not always the case. So we think of a program as a sequence of instructions. So if I gave you a calculator, you would know how to carry on some sequence of instructions. You may have a piece of paper on which you write down temporary results that you get, and you keep following some recipe, but the recipe is written outside the calculator, right? Or it's in your head and you remember it and you repeat it. So I think there was long-term understanding, from 18th century, from 19th century, that program is really a sequence of instructions, even though we didn't have any interesting computers to talk about until 50s. The technical challenge was how to sequence these instructions. So you have a calculator and we know how to calculate, but now somebody says, build me an automaton which will actually go through these instructions automatically, one by one. And that turned out to be a pretty big challenge for people, how to solve this problem. And a lot of time and energy was spent on it. So in the early days, for first few years, you only had a read-only memory, right? So you would have some sort of a diode array, which was actually later. But the thing that stuck for quite a while was you will have paper tapes, right? So you have paper tape readers, which were well developed in those days. And if you could encode your program into that, then the machine would read the paper tape, and that's the instructions, and it'll carry out the instruction. And during that period, when people were exploring all kinds of memory technologies, the idea occurred to somebody, why not have read and write memory for programs also, right? So this idea is spelled out in this paper called EDVAC, which is really a conceptual thing. This machine was never built, but enormously influential, because the paper is extremely well written, right? And had these famous guys, von Neumann, and actually a Kurt Mauchly name doesn't appear on the paper, which is a little bit of a travesty, but whatever. So I think the central idea here is you can store program and data in the same storage. Okay, what's the big deal? The big deal is the moment you think like that, then you suddenly realize, oh, program can be manipulated as data. And the moment that realization came to people, then computers just took off. Because then they say, oh, now we can really write something interesting on these machines, because it was not possible to do something very clever until this realization came that program itself can be manipulated as data inside the machine. And the first successful machine that was built using these ideas was EDSAC at Cambridge University. The connection is very direct, which I'll show you in a second, right? So Professor Maurice Wilks built this machine, and I think it lasted about 6 years. So lots of programs were written, lots of ideas about assembly language programming and design of computers come from the EDSAC days. So what happened is that Eckert and Mauchly and von Neumann have these ideas. They have written this paper. It's all classified. It was happening during Second World War, and this was considered the highest level of secret, because the justification for producing these things was that it can be used for calculating munitions ranges and building atom bombs, etc., though the first atom bomb was built without any computers. So they held a course. The course was taught at University of Pennsylvania. Enormously influential course. Anybody who took that, not anybody, so there were maybe 20 participants or less in this course, and everybody went home and they built their own computers. So it was a big privilege to be invited to this course, and these were already very important people who attended the course, and they went. So At Princeton, IAS was built, Cambridge, ETSAC, Maniac, Joniac, ELIAC, many different machines were built during that time. And MIT wasn't far behind, so MIT built Whirlwind, and its justification was it was a real-time computer, so it was going to protect against incoming missiles. So it was the SAGE defense system. So it was an enormous machine, right? And a lot of work went into it by Forrester and Everett. So in some sense, it was the first real-time computer, right, which could do something. Now, there is another figure in computing which is so important, Alan Turing, right? And he was actually not just a theoretician, he was a great tinkerer. He wanted to build machines, and he wanted to design assembly language and all kinds of encoding schemes, and they were only good for him. I mean, his way of thinking was so convoluted, right? He was optimizing every last bit. But I think the trouble here is, during the war years, it's not clear how they influenced each other, because it's all secret, and then even after the war, people haven't been able to find out very much about it. But one fact is that Turing did spend 1 year with von Neumann at Princeton during that time, right? So they must have influenced each other, except that they didn't like each other. So, and von Neumann was a very established figure at that time, and Turing was this young guy, logician, who, if you have seen the movie, you know what I'm talking about. So, so here is all this research going on and trying to build these stored program computers, right? And there are maybe a dozen of them in the world at that time that are being constructed. So what's happening commercially? So commercially, IBM dominated the scene with calculators. The kind of calculators which most of you will have hard time imagining. So here is a description of this calculator. It has 150 word store, right? Not just 1 or 2 accumulators, 150 words it can store. Instruction, constraints, and table of data were read from paper tapes. Okay, 66 paper tape reading stations. Can you visualize this? You have a calculator which is so big, and you need lots of input going into it. So there are 66 reading stations, right? And data could be output from one stage. You could print out the paper tape, which could be fed into the next stage, etc. Now read this sentence. Tapes could be glued together to form a loop. Loops was a very big deal. People just did not understand how to do loops in computing. And you will come to appreciate this very quickly. I'm going to show you 1 or 2 things. You say, I know how to do this, and then you get stuck. You know how to do this. So this is the idea that is happening and I think ultimately the first commercial computer that was built was UNIVAC, which was sold in 1951, and they got huge mileage out of it because election results were tabulated on this. So, they were on television, which was also in its infancy at that time, right? So they were showing results of 1951 election on this. Now then there was IBM 701, and I write it in a very dramatic way because it changed everything. It changed everything. Notice the first number. 30 machines were sold in the first year. Before that, we are talking of 1 computer in this city, 1 computer in that city, right? We could count all the computers in the world. Suddenly, in 1 year, you're selling 30 computers. Not only that, they designed a cheaper version, which was IBM 650, extremely successful machine, and they sold 120 of them in the first year, and they had back order for 750. So this is a very big deal. I mean, you're going from 1s and 2s to saying, oh, no, this technology is for use, and these machines are not being sold just to engineers. These machines are being sold to banks and insurance companies, which had a lot of data processing to do. Now, in some sense, they took the fun out of it, right? Because now nobody was going to fund you to build your own machines. They buy one from IBM, right? So I think that's what happened, that there was no reason for you to build your own machine because the chances you could outdo IBM that their game was close to zero at that time. So there were other commercial competitors, but in the academic world it became all these research, because it was a very, very expensive affair to build a computer. So people have often asked the question, why was IBM so late getting into the game? I mean, it already knew all this stuff. Why was it not started producing computer in 1950? I mean, how come Univac was the first company to do it and IBM entered the scene 3 years later? And the reason is they were making too much money, right? And when a company is making too much money, your vision gets like this: oh, I can make more money by selling these fancy calculators. Why are you bothering me with computers? I'm already making so much money, right? So I think their success with calculators is what, delayed their entry into the computer business. Now, this is a very important slide, and I want you to pay attention to this. So this is instruction description taken from IBM 650 manual. And this is, as I said, the most popular machine at that time. I mean, the first machine that sold, ultimately the number reached over 1,000 of how many 650s were sold. So you're going to program this, right? And you're not a hardware engineer, you are some guy who wants to program this machine, and you open the ISA manual, and that's the kind of description you will find, right? So can you read this description? Load the contents of location 1, 2, 3, 4 into the distribution, put it also in the upper accumulator, set the lower accumulator to 0, then go to location 1009 for the next instruction. The main point, the takeaway from this is your view of programming is inseparable from hardware. They want you to understand that there is something called upper accumulator, lower accumulator, this, that, and where to place the next instruction in it. Programmer's view of the machine was inseparable from the actual hardware. So if you have two different machines, they're going to program them quite differently because they're going to be different internally. So at that time, if you said, actually, I would like a high-level language. I would like a language in which I don't have to know all these details, you would have been laughed out of the room. People say, are you crazy or something? You mean you're going to program your machine without knowing how many registers it has? Right? So that's the background in which Fortran was developed, right? And why it became such a big deal, because that was the first language in which you didn't have to understand the underlying implementation of your computer. Now, there is always room for hacking. So in this machine, the main storage was on a drum, right? So if you read an instruction here, by the time you are ready to read the next instruction, the drum has moved, right? So if you put the next instruction right next to it, it's very slow. So you can calculate the speed, and you say, if I put the first instruction here and the next instruction where the drum will be when I'm ready to read, then it will be much faster. So that's the level of hacking people were doing, exactly how the program should be spread on the drum so that when the computer is ready to read an instruction, it's right there. Right? Different level of programming, in those days. Okay, so now if we look at the scene in 50s, what's happening with computers, couple of things stand out. One, hardware was extremely expensive, and this thing continued until early 70s. So if you came for a tour of MIT or any other prestigious school, you would have been taken to this building behind glass cases where their computer was, right? It was a thing to display because it was so expensive. You could be proud of the fact, my school has this computer, right? None of that. I mean, that has completely disappeared now, because now we put computers in some remote area which are almost inaccessible, right? These gigantic data centers, but hardware was expensive. Stores were small. Now get used to it. 1,000 words. You're going to write all your wonderful programs and you have 1,000 words. We're not talking of registers, we're talking of the amount of DRAM, as you will call it. There was no DRAM at that point, right? You have very, very small amount of memory. Okay, so one corollary of that is, if the storage is so small, there is no question of any resident software. So you can't even say, oh, what kind of OS it had. What OS? You're trying to run your program, that's going to consume all the memory. So the only actually commonly used utilities that existed for everybody, if you were doing floating point calculation, so there'll be a floating point library, because in those days floating point was not implemented in hardware. It was emulated using integer instructions. So you may have some shared routines, again to save storage, so that everybody can use the same things. Memory access time was 10 to 50 times slower than the processor cycle. Now at that time we didn't know that this kind of a disparity between the computing speed and the memory access speed will continue. I mean, if it's anything, it's worse today, right? We can compute extremely fast, but accessing storage remains very expensive. This was true even at that time. Instruction execution time was totally dominated by the memory reference time. So it didn't matter how long it took to decode or to do your adds. All the question was, just fetching the instruction was going to take a long time, right? And if instruction happens to refer to memory, right, then you're going to refer to the memory again. So memory time just dominated the whole execution of one instruction. The other thing that may surprise you, or maybe not, maybe it's not such a surprise, the main technical challenge in building these machines was design of this controller. The design of this controller. Now you're doing pipeline machines for your project and optimizing it. Believe me, the controllers in these machines are trivial as compared to what you're doing today. Absolutely trivial. I mean, I could give it as homework 1, right? They're so simple, the controller in these machines. But the point is, people did not know how to think about controllers. They knew a little bit about finite state machines, and if you start thinking like that, you'll go crazy trying to design the controller for instruction sequencing. So what I want to do is transition to give you a flavor of what these instruction sets look like. Now remember, the dominant computing model in people's head is a calculator. And the thing that stands out about a calculator is that there is something called an accumulator. Even today, when you calculate, you see there is a number being displayed in the accumulator. And your center of focus is that, okay, add something to it, subtract something, multiply something to it, right? So accumulator, at the end of the instruction, you always get some new value in the accumulator. So this is how computing began, right? So not surprisingly, the earliest instruction sets are all accumulator-based instruction sets. And another reason was registers were very expensive. I'll visualize it for you. So in Whirlwind, you have an accumulator which was 18 bits, right? 18 bits wide. Each bit of the accumulator was big enough so that if something went wrong, you could stand inside it and fix it. Can you visualize that, right? Accumulator, all the circuitry that is going in there, each bit is like a box inside which a human being can get in, to check out if the wiring is right and if the vacuum tubes are working, etc. We have come long ways. Okay, so let's look at the instruction set as spelled out in their paper. So what do you see in this instruction set? Load X, right? So they're always talking of bringing something from the memory. Every instruction deals with memory. So what you're doing is you're giving me an instruction to bring something from the memory into the accumulator, right? And of course you need some instruction to store the accumulator back into the memory. So you have an address and you have load and store instructions to bring that thing to the accumulator. And what is the add instruction? It takes whatever is in the accumulator, it brings something from the memory, adds to it, and leaves it in the accumulator. This is exactly how people thought of a calculator at that point. But notice now, even this add instruction is referring to the memory, because you're always bringing something from the memory, adding it to the accumulator, leaving it in the accumulator. And you can have multiply and divide, and these were, you had to provide one extra register for it, a quotient register. And von Neumann, one of the big contributions to this paper was it offers very convincing argument why all the arithmetic must be done at the binary level. There is no reason to emulate decimal arithmetic. We can do everything in binary because it's more efficient. So if you follow that, then it follows that by shifting you can also do certain kinds of multiplies and divides and so on, and they made full use of it. So the earliest computers had shift instructions in them, essentially as a way of speeding up multiply and divide. And this legacy goes back to Babbage, in 19th century. They knew that for doing control, they need some sort of a test, right? And of course it made sense if the test was done with the accumulator. So accumulator, if it was greater than 0, right, then you put some new address in the program counter. Otherwise you would have gone to the next instruction in the system. Does this instruction set make sense? You can understand it right away, right? And this will become clear why we need some instructions to extract the address part. That means if I gave you that load X instruction, I may want to just look at X from it. So there were special instructions for that. But taking everything into account, there were less than 2 dozen instructions on EDVAC and EDSAC to start out with. Okay, so you're ready. Now let's write a program. And the program is going to be very, very simple. All I want to do is add 2 vectors. I have a vector A and I have a vector B, and I want to put the results after addition into vector C, and the length of the vector is n, right? It's stored in another location, and I will need constant 1, so I have stored that somewhere also. Okay, so see if this program makes sense to you. So you load n, right, the constant, and you jump greater than or equal to 0. If it is that, then you go to done, because we're going to initialize it to minus n. And then you add 1 to it and store it back in n. So that tells you how far you have progressed in your computation. And then I do load A, load B, and I load A, add B to the accumulator, and whatever I get, I store it back in C. Fantastic. And I say jump back to loop. Not so difficult to write, except that this program doesn't work. What is the problem? You see, every time you traverse this loop, you need a different address, right? First time you were doing A, B, and C. Next time you want to do A1, B1, C1. Next time A2, B2, C2, right? So you have to somehow step through the data. Now, I can tell you that if not ever enough hints were given, this will become a PhD level problem, right? And the hint is write self-modifying code. So what can I do? I can look at F1, F2, and F3, because these are instructions. I can look at instruction as a data. And what can I do to these instructions now? I can go and do surgery on the instruction, right? I can change A to A plus 1, B to B plus 1, C to C plus 1. That's all arithmetic, right? Fetch that instruction, add 1 to it, put it back. Fetch that instruction, add 1 to it, put it back. Okay. So this thing becomes so load the address part of F1, add 1 to it, and store it into the address part of it again. So each instruction is being modified now. How many of you are following me? Nobody? Yeah, makes sense? That you have some instructions, and the only way I know how to change that address is to do arithmetic on it, which is allowed because it's a stored program computer. I can operate on instructions like I can operate on other data. So this is how a loop was written. And everybody thought, even I think so, this was the best thing since sliced bread. Did sliced bread exist at that time? I don't know. Okay, so it was a very, very clever thing, because suddenly all this, none of this hunky-dory stuff, you know, with wrapping loops and gluing your tapes together, etc. Because now I'm giving you a systematic way of doing your loops, and you have a test for 0 so that you can get out of the loop whenever you want in it. So let's just do simple arithmetic on this, right? 17 instruction fetches per iteration, right? 10 operand fetches, 5 stores. And how many instructions are for bookkeeping? Out of 17, 14 instruction fetches have nothing to do with the vectors I was trying to add. It's just setting up the computation, right? Bringing it, doing surgery on the instruction, etc. Right? Operand fetches, I'm fetching it 10 times because every instruction fetch has to be regarded as a fetch, right? And 8 of them are overhead. Stores, 4 of them are overhead. In other words, all I wanted to do was to do 2 reads, 1 add, and store it back. But instead, this is the overhead I'm paying. And most of the executed instructions are for bookkeeping. So people said, this is not right. We need to do something. So this became a research topic. What can I do so that I don't have to continually do surgery on these instructions? Okay, so the clever idea, which was introduced by Tom Kilburn at Manchester University, right, was to have more specialized registers, which he called index registers. So the idea would be that, you know, suppose I have 4 index registers, so I can choose IX is one of those 4 registers, so it's taking few bits to specify this register. But now the meaning of the instruction is, instead of fetching from X, add the index value to X. Right? So if you add the index value to X, now I can keep changing it, because all I have to do is change the index register. I don't have to go and change the instruction that is over there. And you can add new instructions which will be checking if the index register is 0, then you jump to somewhere, otherwise you continue in the same way. And you can also load the index register, and you can store the index register, and so on. Pretty soon somebody says, you know, this is a very clever idea, but these index registers are beginning to look like accumulators. You have given me 4 index registers. You want to increment, you want to decrement, you want to test for 0. We were doing all these things. What is the difference between index register and your general purpose register? A very valid question to ask at that point. But at least your program has become much better, because now you're not going to have this, you know, in the middle of the iteration, same instruction being brought out, modify the address, store it back. All that is gone, because now we're just going to change the index register, which is the processor state. So using index register, the code becomes much simpler, and program does not modify itself. Efficiency has improved dramatically, because we are not fetching the instructions over and over again. And, you know, it's fantastic, basically. So the point is, there were no index registers before. Introduction of index registers simplified programming, as well as made efficiency of program dramatically higher. So you can imagine that any machine built after that is definitely going to have index registers in it. Okay, let's go on. Complex control, index registers. All right. Now, if you look at operations on index registers, so these are the most obvious ones. You have to bring the index register into the accumulator and back, etc. You have to be able to add some constants to it. Also, AC must be saved and restored. You need to increment index registers. You need to store it. Began to look like a accumulator. So people say, all right, in my machine, I'm not going to draw any distinction between index registers and general purpose registers. So instead of thinking of these are the 4 index registers and these are the 4 or 8 or whatever general purpose registers, I'm just going to give you a set of registers and give you addressing mode so that any register can be used as an index register if you want, to do the computation. So this is how the idea of a general purpose register was born. And remember this is a very important lesson in computer architecture, that any time you introduce specialized registers, specialized anything, you can't do anything with it unless you also introduce instructions to manipulate that state. And if you don't want your instruction set to keep growing, you either think in terms of general purpose registers, or in RISC-V you'll think in terms of CSRs, which is another set of registers, or you think in terms of addresses. That's where memory mapped I/O, right? So all the I/O devices, we don't want to have instructions for dealing with every conceivable I/O device. We say, oh, when I write in location 2043, what I really mean is the printer. Okay, so you do this kind of address mapping in order to talk, with all kinds of things without having to change the instruction set all the time. The instruction set will remain simply load, store, and register to register operations. Okay, so support for subroutine calls, they recognize very early on that they need subroutines, and the idea is that from 2 different points you're jumping to the same code, so you have to go there, come back here, from here you go there and come back here, and you don't want to copy this code, so this remains where it is. And Wheeler, who was one of the programmers, a professor at Cambridge, right, he showed how he could execute this code without anything special. So he took self-modifying code to the next level. He did some hacking, which I used to give out as a problem set a long time ago, but I'm not going to bother you with this. But there's actually a paper published on how to do this stuff without the thing. And after that, this jump subroutine instruction was introduced, which was also his idea, that when you jump there, you remember where you came from. So we store it in some register. So you have jump and link, that's how RISC-V and all modern instruction sets work. Now, even after doing that, there was a problem, because I jump into the subroutine and I have to do some relative addressing because the arguments were here, right? In my code, they're sitting here. So sometimes call came from here, some other time the call came from here. So when it's saying load the first argument, it's not the same address. We are back to square zero. Should I go and modify these things every time, I call the subroutine? And that's how the idea of indirect addressing was born. That we will leave the address somewhere else in the memory, and whenever you wanted to access something, you could say, no, I don't mean that, I mean the contents of X. So that combined with, indexing could let you access anything. So these 2 things are so important in modern instruction sets. You do this indirection through registers and not through memory locations, but the idea is the same. So indexing and indirection are sort of the backbone of any instruction set. I mean, it will be hard pressed to find an instruction set that doesn't have those 2 capabilities, as well as some sort of a jump and link instructions. I'm not going to go through all this. All right. So as you can see how the addressing evolved, right? So first you have just the accumulator, bring X, and I don't even specify where because there is only one accumulator, right? And then we have it with index registers, and then we have with index registers, and then we have the works, and the final through is indirection through registers. All right. So what I've convinced you so far is in order to program these machines, you have to know how many registers are there, and how wide they are, and where the address is, etc., etc. I have to know lots of details about the machine. Now, IBM was just going gangbusters in 50s, right? Very, very successful company. It had an internal problem. It had 4 completely different sets of computers, families of computers: 701, 650, 702, 1401, etc. Systems had, every computer had its own instruction set, its own I/O system, its own assemblers, compilers, libraries, and they were intended for different markets. So IBM said, this cannot continue. We cannot maintain so many different lines of computers because there is some commonality and we must find a way. So, for example, why shouldn't the I/O be the same for all of them, right? Same printer should work, same software should work, so this was the origins of 360. So they were solving an internal problem. They were trying to do something so that they will have only one ISA which will serve all their computers, so they say you can have different implementations. So they are way, way, way ahead of the game in this. No other competitor was thinking remotely like this, but IBM was thinking in terms of. So really, this was the first attempt to define an instruction set without referring to an implementation, without saying anything about exactly how many things are inside it, whether it's pipeline, not pipeline, what registers exist, except for architecturally visible registers. So this is how the definition was given. And this is a fantastic paper. I highly recommend you should read this 1964 paper by Amdahl, Brown, Brooks. Okay, and they defined many things which we stick to even today. So for example, they said there is a notion of processor state. This is what we call architectural state. What is the processor state in RISC-V? Yes? Processor state is something that is visible after one instruction to the next instruction when it executes. What is that information? Yep.
The values in all of the registers.
Values in all the registers plus PC, right?
That is a register.
Yeah, okay. And memory also. Right, because we rely on the memory. We say if this instruction did something to the memory, it has to be visible to the next instruction. So all these abstract concepts of what state you can rely on, which we call architectural states, they were defined in the IBM this article, program counter, accumulator, etc. And then they also said every instruction assumes a bit pattern, right? So whatever, if you say it's an integer, it's implicit at that point, whether it's a 2's complement or 1's complement or whatever, right, bit pattern. So data types are also sort of being defined at a hardware level. If it's a floating point instructions, then you're going to interpret those bits in a certain way. So you don't carry tags there, it just goes and looks at it, right? And they talked a lot in that paper about why not tagging, right? It's not a good idea as far as they were concerned. And then look at this. If an instruction can be interrupted, then the hardware must save and restore the state in a transparent manner. So why are they thinking of interrupts in such a big way? Because of I/O, right? I/O is so slow that if I have started something there, I don't want to sit here and twiddle my thumbs. I'm going to go and do something else on this computer while I/O is going on. So I need to restore the computer program that started this I/O. So therefore I need a very precise notion of interrupts, that I had executed every instruction up to this point and I haven't done anything beyond that. So the notion of precise interrupts was defined in this machine for the first time. And it was so important, that they said it wouldn't matter which computer you're running on, you'll see the same interrupt behavior on that. So programmer's machine model is a contract between hardware and software, which is what we have been saying over and over again. Okay, so we don't have time, so this is the kind of instruction set it was. It's pretty simple, but it's extremely memory based, right? So unlike the RISC-V instruction you have, where almost all the instructions just deal with registers, here the basic instructions are always you're specifying a register and you're specifying an operand that comes from memory side to do something with it. This is something we haven't touched on at all. So RISC-V has a style of branching which is extremely popular, that you compare the value of the accumulator and you say if it's 0, do something, otherwise do something else. Or you compare two values and depending upon the result you do something. There is a completely different style of branching which IBM adopted, which is I do some arithmetic and I have another set of registers which are called condition codes and I set those. And all the branches are based on condition codes. I go and look at those things and then I can jump based on that. And if you look at it like that, there are some advantages because you can do interrupts in a very interesting way, you know, because then if you get an overflow, underflow, you can set those bits and you can test it and all kinds of things can happen because of it. So this is the most important part. So this paper is published in 1964 and at the same time IBM announces 6 different models of the computer with 6 different speeds, 6 different price ranges, right? Very, very different from each other. But the promise that any program that runs on one is guaranteed to run on something else. A promise that is held by IBM until today. Right? So they really designed something, they mastered the concept of abstract idea of an instruction set architecture so that you can keep innovating underneath, you can keep going and designing better and faster machines. It is still in use today, right, this instruction set. So this is the picture of a microprocessor which came out a few years ago, which is still running 360 or its successor, you know, it's 370, 390 instruction set. Look how far we have come, you know, from it. You know, 1.4 billion transistors, quad-core design, right? Up to 90s. I mean, it's just amazing. Even IBM people could not have imagined in 1964, you know, that 50 years later, this instruction set will still exist, right? Exist, and you know, people will implement it. So that shows you that if you do a good design, and this is absolutely true, if your instruction set is worth anything, it's going to outlast any implementation, right? Because you're going to keep building newer and newer implementations all the time, but it has to run old programs on it for sure. Now RISC-V ISA is much simpler than ISAs from the 60s. Why? So this is the thing I do not want you to forget. So somebody says RISC stands for reduced instruction sets. In fact, to me it's a misnomer to call it a reduced instruction set because even EDSAC had only 20 instructions or 18 instructions, so we are certainly not smaller than that. I think what makes modern instruction sets or reduced instruction sets interesting is there is an absolute division. There are instructions that manipulate registers. R1 plus R2 goes to R3. There's a whole slew of instructions. They never talk to memory. And then there are only 2 instructions that talk to memory. A load, which brings something into the general purpose register, and a store that takes something from the general purpose registers to the memory. So this separation was achieved first by Seymour Cray in 60s, right? He is the first one to design machines like that. But now it's gospel, except for Intel machines. So x86 still doesn't follow this philosophy, but that's for compatibility reasons. But everybody agrees that this is a great idea, to separate load store instructions from other register to register instructions for the simple reason register to register instructions have a very well defined boundary. You're doing something inside, right? The moment you do load and store, you're going outside, you're getting something to bring it back. To this day, it is true that when you go outside and get something, it takes a while. So we spend a lot of time designing caches, this, that, to create an illusion that it doesn't take so long. So there's a great complexity in memory systems. But at least at the implementation level, we have simplified the problem. We have simplified the problem that we can look inside and we can pipeline it, we can do all kinds of crazy things, we can do superscalar execution, etc. And separately we can keep designing memory systems, which can do many loads and stores simultaneously in them, because the most important aspect of memory systems is that it should be able to tolerate more than one load miss, more than one cache miss. If you don't get a hit, now you know it's going to take a while. So what will be great is if you can do another load instruction which gives you a hit, or if it gives a miss, then you're processing two misses simultaneously. The moment you can do that, which is necessary for all fast machines, then things work very well. So it makes it easier to implement when you have such a clean divide. Well, I'm going to stop here. So I hope you have enjoyed this class, especially the labs and the project, because if you have done labs, you can be very proud of the fact, but what you have accomplished in terms of design, really it's not common. People in other schools and other places will be surprised by the degree of sophistication you had in your design. So that's the heart of this course, that you have to do these labs properly, and we want to thank you, because this course cannot be taught if there are no takers, right? So I know some of you may be taking it under duress, but it's very important for us. We need the feedback to figure out. So thanks a lot for taking the course and doing the labs. Good. I'll be happy to take any questions or comments if you have. The team was extraordinarily strong. You have heard so many lectures from Silvina and Daniel, and that's just the surface. What goes on behind the surface, behind the curtain, is much more collaboration, and without TAs, the course just cannot run. You guys, they are our primary interface to you, and I think you like them generally because you want more time from them. So any other comments? Any announcements for the quiz? So when is the quiz? Is a week from this Thursday, right? A week from this Thursday. So now you can go out and play, or if you want, you can prepare for the quiz, whatever, right? You don't have to worry about this lecture. Very good. Thank you.